Alright, so this theorem is order limit theorem, and this is one of the nicer theorems because, well, in my opinion, it is one of the nicest theorems because if we prove the first part of it, then the second part is going to follow from the first part, and then the third part is going to follow from the second part's results. So let's dive right into the theorem. The theorem states that assume limit of the sequence an equals a, and the limit of the sequence bn equals b. The first part states that if each of the term in the sequence an is greater than or equal to 0, then the limit of that sequence is going to be greater than or equal to 0. And the second part states that if the limit, if each term of the sequence in an is less than or equal to the corresponding term of the sequence in bn, then the limit of sequence an is going to be less than or equal to limit of the sequence bn. And the third part states that if there exists a real number c such that that real number c is less than or equal to every term in the sequence of bn, then c is going to be less than or equal to b. And similarly, if there is a c that is greater than or equal to each term of the sequence in an, then the limit of that sequence an is going to be less than or equal to c. So let's dive right into the proof. So the proof of the first part goes like this. Let epsilon greater than 0 be arbitrary. Assume for contradiction that the limit of the sequence an is less than 0. Let's assume for contradiction that the limit a is less than 0. Then what we have in the picture is that, let's say this is 0, and limit a, the number a is something less than 0. Let's say something like this. And then each term of the sequence in an has to be greater than or equal to 0. So it has to stay in this part of the number line. Let's say something like a1, a2, a3, and so on and so on. It will never be in this section because each term has to be greater than or equal to 0. So, and let's say this is some epsilon neighborhood of a. So we're saying that when each term of the sequence is greater than or equal to a, we're saying that the sequence an converges to a that is less than 0, which is not possible, as you can see in the graph. So we'll yield a contradiction by assuming this absurd property or condition. All right, so we let epsilon greater than 0 be arbitrary. Consider the particular epsilon naught to be absolute value of a. Since a is less than 0, absolute value of a is going to be greater than 0. So that allows us to choose epsilon naught to be greater, to be absolute value of a. Then, since the sequence an converges, there exists big N in the natural numbers such that whenever small n is greater than or equal to big N, it follows that the absolute value of an minus a is less than absolute value of a. Well, this implies that an is less than 0 for n greater than or equal to n. Hence a contradiction, since we assumed an to be greater than or equal to 0 for all n and n. So that's a contradiction. Therefore, the limit a must be greater than or equal to 0. And to see this y in more detail, consider this visualization above. Since we let epsilon naught to be absolute value of a is just the distance between 0 and a. It's just that positive distance. So this is actually what's going on. This is the epsilon neighborhood in this case. And we're saying that the distance between the term an minus the limit is less than absolute value of a. So which means the terms has to be inside here. It has to be within the epsilon neighborhood. But that's not possible because each term of the sequence in an is going to be greater than or equal to 0. So it has to be outside here. Well, that's a contradiction. immediate contradiction we have. So that's the contradiction we produced to show that the limit actually has to be greater than or equal to 0. All right, what about the second part of the proof? We want to show that if an is less than or equal to bn for all n and n, then a is less than or equal to b. So we'll copy that here. If an less than or equal to bn for all n and n, then a is less than or equal to b. Since an less than or equal to bn for all n and n, we know that bn minus an is greater than or equal to 0 for all n and n. Well, by 1, the limit of bn minus an is going to be greater than or equal to 0. By the algebraic limit theorem we proved previously, since bn and an are both convergent sequences, we can say that b minus a is greater than or equal to 0. Thus, a is less than or equal to b. And that's the end of the proof of the second part. So it follows nicely from the first part and also the algebraic limit theorem. What about part 3? Part 3 states that if there exists a real number c, such that c is less than or equal to bn for all n and n, then c is less than or equal to b. We'll just prove this first statement because the second statement is very similar. It's just going to follow immediately. So let c and r such that c is less than or equal to bn for all n and n. Consider a sequence Cn to be just a constant sequence. Then Cn is less than or equal to Bn for all n and n, obviously, because each term is C, and we know that C is less than or equal to Bn for all natural numbers. We have that. Then by 2 of the order limit theorem, it follows that C is less than or equal to B, right? Since the sequence Cn is less than or equal to Bn for all the natural numbers, by the order limit theorem 2 we proved up here, it follows that C has to be less than or equal to B. And that's the end of the proof of the order limit theorem.